All right. So we have completed LU decomposition last time. The basic idea is it's really, I would call LU decomposition a strategy. Okay? Gaussian elimination is sort of the parent algorithm or parent method here. And the reason why we are strategizing is that we will, during the process of forward elimination within Gaussian elimination, we can actually record matrices L and U. L is lower triangular, U is upper triangular, such as this example. And if I record them and save them, okay, and I know I'm going to be solving a problem AX is equal to B multiple times with the same A, that can save me some time in computation. Okay? So I expect you, and that's part of your homework, to be able to modify the Gaussian elimination algorithm that we did in class, modify it so that you can actually record. What you end product of forward elimination is this matrix U, right? So if I'm asking to record it, I should just be able to record it and maybe give it back as an output of the function. Okay. So I should be able to split those, or rather you should be able to split that, and also record these coefficients and as you're stepping through. So there's multiple variations of a Gaussian elimination that you're asked to do. Again, there are variations of the code you already have. You can always improve on what we had, but we had it in class. So essentially, LU decomposition or recording things to make it happen. Then we have back substitution already programmed, so you can use that. You can separate it as a separate function if you'd like. Okay. There's no problem doing that. And it's a great exercise to actually figure out how to do forward substitution. It's very similar to back substitution. Okay. So you can actually check your understanding that you can actually figure out a for loop that will do that. So those are all examples that you need to do for your comma.
For the 8 inverse, do we have to do it each row individually, or could we do it the identity matrix next to the matrix and then solve it?
So I would expect you on this exam to do the things individually in this procedure. And the reason is because I would expect you to program it this way. So sometimes there's like a procedure. All of these procedures that you do by hand, they look in a certain way because they're easier to do by hand that way. And this is something that is more amenable for programming. And that's why we're focusing on these steps. So this is slightly different than what you did in your linear algebra review in differential equations. Yes?
So the result of LU decomposition in the columns x1, x2, x3, which is 8 inverse.
Yes.
Okay, so on the homework, for like number 2, it says 2a is like solve using LU decomposition, and then 2c is compute the inverse of matrix A.
Yeah.
So those are both the same.
No. So basically, first problem you would just do this. There's AX is equal to B, right? So you would do this. Okay. Now in that problem, you have already recorded L and U. Okay. So this part is done. And you're just repeating this time. You're first doing this once, okay? And then for A inverse, you're doing it 3 additional times, without the need to replace to do LU decomposition. And that's the whole point.
Okay, so when it says just solve using LU decomposition, you're only finding the first column.
You're doing this once, and this you're repeating as many times as you need. So for A inverse, okay, this is your A remains the same. But you are solving 3 additional systems where you have 1, 0, 0, 0, 1, 0, and 0, 0, 1 as your B. Okay? So you will just replace these steps 1 and 2, which should be 3 and 4.
Inverse A. So then when it says compute the inverse of matrix A, what is
so your inverse of matrix A, first column is this, solution to this. Second column is this. And third column is this. So put that's 3 columns of 1, because that's how we got here.
Right. I was just wondering if you had to repeat the same process again.
No. You just solve this these three systems with these forward and back substitution using L and U that you already have. And that's the whole point. You saved yourself time. Okay. All right. More questions? Now, you know how to do homework. You just need to sit down and do it. Those are not necessarily the same thing. All right. So now we will move on. So we have two more topics essentially in linear systems. One of them is finding matrix norms, and we will see why does that matter. If you remember, vector norm was telling me some sort of absolute measure of a vector. Vector is multidimensional. I typically have an array of numbers, and I want one number that describes it, because that one number helps me compare two different vectors. Similar happens for matrices. So we are going to define different norms for matrices. Which norm you ultimately use in any problem is not so much important. They're all somehow actually related, even though one matrix can have three different numbers or three different values for three different norms. Ultimately, what makes really the difference is like how large that norm is. So if one of them is large, all of them will be typically large. And large, where's the cutoff for large is also a little the boundary is not clear. But regardless, it's still a very useful measure, because matrices that have very large norms, and we will compute something called condition number for a matrix, which is a norm of a matrix times a norm of its inverse. That specific measure tells me how difficult this problem will be to solve, to use in solving linear systems. And when matrix is difficult, but that I mean is that it's going to cause a lot of numerical error. And those are typically matrices, so you know inverse doesn't exist for all of the matrices. But there are cases where inverse kind of barely exists. And in those cases, they're very close to being what we call singular in algebra. Those problems are extremely difficult to solve using Gaussian elimination or any other method. So in that sense, norm of a matrix will help us evaluate how difficult the problem is. And it's so much a problem because I already motivated at the very beginning that solving linear system, basically solving every differential equation in one way or another ends up being solving a linear system. And if it's non-linear, then we typically linearize it. So either way, you end up with a linear system. Okay, so a lot of numerical methods ends up being just solving linear systems. It's so omnipresent. Most of the time, you don't kind of notice it because it's built into the method, and method has a different name. Okay. That it's actually very important to there are people who spend their lives what's called preconditioning systems to behave better in these numerical solutions. Because if it's constantly causing trouble, and you have to, for instance, in reservoir simulation, you're constantly doing it, then of course improving that can help. So this is just a slight motivation for what what we are going on to say now. So basically, just like we had L1, L2, L infinity, didn't you like those for vectors? We have norms that are equivalent to those for matrices. Most common is so-called Frobenius norm, where I will simply reshape a matrix into a vector and just compute the norm of it. Okay. So that's what that happens is like if I take all of the columns of my matrix and stack them into one column vector, all I would do is like I would just take squares of all of those numbers, sum them up and do the square root. Well, that is so-called Frobenius matrix, Frobenius norm. So that one is easy to compute. It's not directly L2 norm though, okay? So the way L2 norm or any other is defined is a little cryptic. What this L2 norm says is, okay, when I think of a matrix, every matrix defines a function or a linear operator that takes one vector x to another by simply multiplying a and x. Okay? So if I have x, ax is another vector, so this is a vector to vector linear, basically linear operation vector to vector, which is a direct generalization of just doing kx plus L, just a line, right? Then I do these scalars. So it's, if I understand my matrix as operator, then I wonder if I take all vectors which their ends live on a sphere that have radius or length 1. So all of those vectors are basically point to a sphere. Let me see, what does this matrix do to all of such vectors? Where do they end up being? So maybe if I'm having some sort of shearing, maybe it's going to end up some sort of ellipsoid after I'm done. Well, so the norm 2 of A is simply finding the maximum value where this transformation AX takes a vector that has length 1. So if this, for instance, in a very simple world, if I have spheres, so all of my x's live on a sphere of length 1, radius 1, and my A is a matrix such that it has that 2's on diagonal, 2, 2, 2. When I do AX, I'll end up just multiplying all of the values of the vector by 2. Right? Does everybody see that? So if I'm mapping a sphere of radius 1, and my A is a diagonal matrix, okay, with 2, 2, 2, I'm going to end up on a sphere of radius 2. Right? So my norm of A will be 2, because the maximum of such, maximum length of such is 2, of such mappings AX. Does that make sense? So this is one very simple case. In a non-simple case, okay, it's a problem. I would end up with this cloud of vectors where my A sent all of the possible cases. Right? And in that case, I'm just going to find the maximum of those, and that's going to be my norm 2. Now, will I actually ask you to compute norm 2 of A? The answer is no, not yet. Because it's not something that is easy to do by hand. You could come up with a little algorithm or how to compute it for yourself if you reasonably take a reasonable number of points on a sphere and just see where they go, take the maximum of it. So you could come up with a little algorithm, a little for loop in there that would do that. That's fine. I'm not gonna do that. But luckily, L1 and L infinity norms are relatively easy to compute. So what I will do for L1 norm, I will take, so if I fix a j here, Aij is all of the column elements in j column, right? So when my I goes from 1 to m, I'm basically going down the one column, and I'm taking absolute values, and I'm summing them up for each column. If I have n columns, I will have n such numbers, okay, and I will find the maximum of them. So that is my norm 1 of A. Norm infinity of A is doing the same, but for rows. Okay. Let's do example. So I have an example matrix. Here's your A. Take this as an A and compute. So your A is 143252. Whoops. 362. I want you on a piece of paper to compute norm 1 and norm infinity. So, as I said, So just put it here so you have those formulas. Oops. So what is norm 1? 11. So let me double check. 1 plus 4 plus 3 is 8. 2 plus 5 plus 2 is 9. 3 plus 6 plus 2 is 11. Maximum out of that is 11. What is norm infinity? Maximum between 6, this is 9, 15, and this is smaller, so it's 15. Okay. Let's quickly check. Of course, MATLAB has a formula for it. 11. So in MATLAB, you can actually do norm of A. You can actually compute norm 2. And that is 10.26. Again, this is not easy by hand. And so this is just 2 examples. Great. So that is one example. Now, my matrix condition number would be computed from matrix inverse as well. So if I have information on matrix inverse, and by now you know how to find matrix inverse, then in this particular case, actually, this is the matrix inverse. I would be able to compute the same for my A inverse. Okay. So in this particular case, so I actually obviously did not use, when I don't specify which norm, typically it's norm 2. Okay. But you should actually specify which norm you're using. So if I had, I'm going to simplify my life, and this inverse of A, I'm just going to use, so if I do norm of inverse of A, 1, okay, that is 6.3, so it's 19 over 3. So 19 over 3 times 11 would be my condition number. 11 was norm of A, right? So it would be close to 70 in this particular case. If I did the same for the norm infinity, there's of course condition number is programmed already in MATLAB as well. So this is my condition number of A in norm 1. Condition number of A in norm infinity is about 115, and condition of number of A in norm 2 would be 56. So we see a range of numbers between 50 and 120. Give or take, they're on the same order of magnitude, and that's what really matters. Because what condition number tells me is the reason why we actually want to compute these numbers is the stability of solving my systems. So it essentially gives me a bound on if I say that I have a system that behaves well. And let's say that I'm actually in the business of designing a chemical reactor. So we had that at that example both in class and in homework. So essentially, you're flowing things in between reactors. You have a matrix that actually describes that flow, and you either solve for concentration of stuff or for the flux of stuff in between. Okay? So basically, what I'm wondering is, okay, a good system or a well-designed system is such that if I change some of these fluxes slightly or some of these buckets as I change ever so slightly, then the change in my ultimate solution shouldn't be big either. If I cause by a small change in my description of the system, I cause a big change in the result, that's not a stable system. There's something in there, there's some sort of a bottleneck that I shouldn't have. So condition number is actually check on you that you don't have such a system. And mathematically, if you have a solution to AX is equal to B, then let's say that you're changing things ever so slightly by changing parameters in A, okay? Then your new solution should not be very far off from that matrix or the measure of that change in the matrix. And condition number kind of relates those two changes. So I changed my A, my parameters, my sizes of my pipes here a little. If I change the sizes of pipes by some delta A, or not much, that should not impose a big change on my system. If a number here is 1 million, however, okay, then this could really change big time. So relatively small condition number ensures that if I make a small change in my piping, I will have as a result a very small change in my flux through those pipes or through concentrations of stuff going through that stuff, the piping. So that's what I physically mean by a well-conditioned system. And believe it or not, if this condition number is large, you could actually have large fluctuations in the result. So some examples of bad matrices are here. So fire up MATLAB, let's just do this quickly. And so there's A, C, and B. And the only difference between A and C is by 0.1 here. So I changed only one number by 0.1. Less than 10% of this number, okay? So the change in parameters, one of the pipes I changed by 10%. That's not a big change. Because I had to replace it and hardware store and only slightly larger size. So let's type in A. Very inventive A. 1, 2, 3, 4, 5, 6, 7, 9, 9. And my C is the same. I'm just going to have 9.1 there. So how will I just use MATLAB to solve AX is equal to B? Backslash operator. So my X is a, okay, whoa, large numbers there. And already MATLAB issues me a warning. Matrix is close to singular or badly scaled. Results may be inaccurate. Now, if I try solving that ever so slightly different system, C/B, I'm gonna get 10 to the 3. So this is a badly conditioned system. I changed one number in that matrix A by less than 10%, okay, 0.1 is less than 10% of 9 last time I checked. Okay. And that small change, even though I'm solving two very similar systems, solution to one of them is on the order of 10 to the 17, and the solution to the other is on the order of 10 to the 3. That is 14 orders difference. You don't want to be this engineer. Don't, don't engineer a flow loop like this, okay? Not a good idea. And let's see whether condition number of A really tells me, yep, I get this huge condition number that actually tells me that, yeah, I'm within bounds, if you will, of the condition number imposed. And this difference in the system, so basically this change in the difference between the two solutions is bounded by condition number. It's just the condition number of 10 to the 16 is not bounding anything, okay? Not limiting anything, really. It's unlimited. So that's the problem, and that's why I want to compute the condition number. All right. So again, if you're engineer designing a flow loop or whatever it is that you're designing, you do want to actually check that it's a well-designed system, or otherwise you might want to try to change the piping or radii or whatever it is, because there's a little bit of an instability in the system that's not well found. All right. This is just an example how it will. So we're not going to actually spend time on interpolation. This is just a quick introduction of what is done. So often for polynomials, I'm trying to find a polynomial that is approximating a bunch of points that I have. So if I were to do that, actually let me just so basically if I just had a very simple system of 2, okay, trying to fit this system would basically be the same as trying to fit a line through these 2 points. Means that my point 746 has to be P1 times 200 plus some P0, and I'm looking for P1 and P0. And trying to do this 0.675 is P1 times 250 plus P0. So what is the system that I'm solving here? If I'm looking for P0 and P1, what is my A? 201 and then 251. So can you, and since these are some measurements, right, that I had in the lab, and I can see easily how one is pressures, the other one is some sort of flow rate, and those are in vastly different units, and I could have any type of numbers here. So that could easily actually create these matrices that are not well conditioned. So can you quickly type in this matrix and see what its condition number is? What are you getting? This is getting large. Now if I was actually trying to fit more than 2 points, so 2 points is easy. If I was fitting more than 2 points, for instance like this, okay, I would have a system P1 times this to the 4 plus P2 times this to the 3 plus P3 times this to the 200. So my matrix would have a range of these numbers, and basically my coefficients are powers of 200, and then my second row is coefficients are powers of 250 and so forth. So that creates actually a very bad matrices. And that's the example of so-called van der Monde matrix here. So those type of matrices are ill-conditioned as well. Okay. But I can obviously see where I was trying to kind of interpolate some data that I got in the lab, and that does not necessarily go well. Okay. So those are some example of badly conditioned systems. We have basically gone through all of these systems, all of these examples. So we exemplified them all. LU, I did not do in class. If you want to check on yourself, you can. Be careful though. By default, MATLAB will do pivoting. So you have in your homework pivoting and no pivoting. And pivoting I can do not only if I encounter zeros on diagonal, but also if I encounter small numbers. As a precaution for dividing, I don't like to divide with very small numbers because that will cause numerical error, and it only kind of piles up in these type of computations. Pivoting is done by default just to reduce any kind of numerical error that you will have an example for in your homework. Well, MATLAB will do it by default, so this P essentially records any switches in rows and columns. So you can see kind of how different P is from identity matrix, tells you which rows were switched. Okay? So if there was no change that MATLAB did to A in switching rows or switching columns, then P will be identity matrix. Otherwise, it will switch things up. So that enables you to track things down. So this result that MATLAB gives might be slightly different than whatever you find by hand with the algorithms that we outline. So just be warned. Don't be upset if you find a different solution. Ultimately, we know that LU decomposition is not unique. So you could get different lower and upper diagonal matrices whose when I multiply them, I get the same A. All right. So just as a recap, we can go on through Gaussian elimination and what I call a strategy, LU decomposition, that is trying to be smart about how you do Gaussian elimination for multiple systems. And these are so-called direct methods for solving a linear system. And typically I have forward elimination step to get to an upper triangular matrix, and then a substitution, back substitution to solve for the ultimate solution. Some pitfalls is that these are slow for systems that are larger than a few hundred. So we actually saw that exercise for 1,000 and 2,000 that I asked you to do with your code. You can easily get into hours needed to solve a system. And this round of error that I have from constant multiplication and division and addition and subtraction while doing these methods, if I'm doing it for a long time, there will be more numerical error will pile up more. So because of that, we actually need an alternative for large systems of equation. So typically cutoff is about 1,000. For more than 1,000 by 1,000, you will not do Gaussian elimination. What you will do is so-called iterative methods. Okay? So this is an alternative. Just like in finding roots of an equation, you basically look at your equation and try to figure out if there's a way to start with some number or some numbers and try to get closer by iterating to the solution. And the basic idea of how it's done is, okay, here's my system. Let's say that I have a 4x4 system. The system is 4x4. I can actually try to simply express x1 from the first equation, express x2 from the second equation, express x3 from the third, and x4 from the fourth. And if I do that, I'll get the following. So I didn't do anything to the system, it's still there, ax is equal to b. I just kind of rearrange things a little. Now, I have x1, x2, x3, x4 on one end, and some combination of x's and my matrix A and coefficients B on the other. And somebody looked at this and said, it was Gauss again, let's try to use this to create an iterative method. I start from any x0 that I can come up with, and I plug element. This is a vector. It has four numbers here. And let's just put those elements in here, compute this part, and this is going to be my next iteration. Then I'm going to take this, which is my iteration number 1, and put it on this side and compute my second iteration. And since I have a for loop going in my program, I'm just going to keep going. And since I kind of got this by rearranging ax is equal to b to begin with, maybe that's a good way to find the solution x to that system. When will I stop? So I have a for loop. I'm programming. I can throw this. I can program this. When will I stop? When do we stop in root finding?
Error is small enough.
Error being the difference between two iterations. It's small enough. I measure what it is. So at the end of computing this, okay, I find what's the difference between previous step and current step. And if that difference gets small enough, well, I'm kind of closing in on a solution. So I have a numerical method. Who knows whether it works? Well, there are ways to actually figure out, but this is so-called a Jacobi iterative method. It can actually work. We will get to when. And there are two variations of it that are trying to speed up this one. So the moment you have a numerical method, there's a way to speed it up as well. So these are basically, so we're gonna, this is the parent method, so to speak, and these two methods are speeding up. So I have 2 minutes. I can introduce what we're gonna do last time. So this is what I came up with, and of course I want to program it. If I want to program it, I want to write a nice little for loop. So I need to know how to translate this, okay, into a cryptic looking sum, okay, that I can actually program on a computer. So when I see I have x1, okay, there's always going to be b1 here. If I have x2, there will be b2. If I have x3, there will be b3. If I have x4, there will be b4. So as a rule, if I have xi, I'm going to have bi on this end. Okay. And I'm dividing by aii. Yes? So that's right here. I'm dividing by aii. And then I have a sum. I have bi minus some sum. Okay. I need to form this sum in terms of i's and j's that I can go through, because that will allow me to write a program that basically solves this in any general situation. What I can notice is I have, in this first row, I have a 1, 2x2, a 1, 3x3. So I have 2, 2, 3, 3, 4, 4. The one that is missing is 1, 1, okay, because it's over here. So basically this is a sum of aijxj's, as this j is going from 2 to 4. So basically all of the j's except for the first one. All of the j's except for the first one. Now, this is a cryptic way. I don't expect you to write it in 2 minutes. We will actually go through steps next time. This is just how we're gonna get to programming this method. Yes.
Just to clarify, I think there's a mistake in the last export, 3K41. No, on 4 on the top.
This one?
Yeah,
4-1, yes.
okay. Sorry.
This is taken from a book, like it's a picture. So yes, I